Okay, so good morning, everyone. So am I audible?
Yes, sir.
Yes,
Good
sir.
morning.
So let's continue our discussion on electromagnetic theory. So uh, I will first write down this Maxwell's equation because that is those equations are the most important, the fundamental equations of nature that has been compiled in a systematic or nice way by Maxwell. So the first, and I am writing it in space, okay, in free space. So this is the differential form of the Maxwell's equation, which are most commonly known uh, in physics. So del dot B is 0, then equal to minus del P by del T, curl of B plus. So what these equations?
Durga sir, good morning.
Good
This is
morning.
Dr. Panigray from IGNO.
Good morning. Yes.
So you have another class at 4 o'clock in evening.
Yes, yes, yes.
Continue, sir. Thank you.
Okay. So you have these. So the first equation is the Gauss's law. The second equation is the Gauss's law for magnetic field, you can say. Uh, the third one is your Faraday's law of induction. And the fourth one is your modified Ampere's law. So the Ampere's law, basically, you can say curl of B will be up to equal to mu naught J. That is your Ampere's law originally, but Maxwell modified it and added this second term, which indicates or which is essential from the symmetry point of view, as well as to account for a particular or which symmetry point of view, in the sense, like as we said, the third equation shows that a changing magnetic field, a time varying magnetic field, can produce electric field. So similarly, a time varying electric field can produce a magnetic field. So this is what this modification by Maxwell that was included to complete the all the equations or laws of electromagnetism. And that basically, once this all these equations are put in this form, so completely it is known as the Maxwell's equation for electromagnetism. Now, also there is a continuity equation, which is your del dot J plus del rho by del T is equal to 0. So which is your conservation of charges. So this continuity equation indicates conservation of charges. And also what we can further do is, like for a charge free and current free region, you can write this equation. So a charge free and current free region means rho equal to 0, J is equal to 0. Okay, so current density is 0. So in that case, you can write these four equations. It becomes much more simpler. So del dot E is 0, del dot B is 0. So curl of B remains minus del B by del T, and curl of B is equal to, so the first term here will, the mu naught J term will be 0, and you have only the second term will be there. So now if you take the curl of this, one of this equation, third or fourth equation, so what you will get, a del square E is equal to mu naught epsilon naught del square E by del T square. So which similarly for B also you can write something like that, del square B by del T square, which represent a electromagnetic wave equation. Okay, so this is from just simple electromagnetism. So when we look at the Maxwell's equation in charge-free and current-free region, so these electric fields and magnetic fields, they can sustain and they can even travel. Okay, so without any source or anything, so they can even travel just like a wave, and which is represented by this wave equation with speed which is equal to the speed of light. Okay, with this speed, so they can move. So this is what the interesting part or extension of Maxwell's equation, so which unified your electricity and magnetism and said they are basically the same thing, although in a form of equation, and when they appear physically they might be different, but fundamentally their origin is exactly the same. And in fact these electric field and magnetic field, they constitute or they can propagate just like a wave. And this is not only just any ordinary wave that we think of, it is just this wave that we see every day in our life, for example light, sunlight, or any light that you see. And there is a spectrum of this wave, so starting from your radio wave until X-rays and gamma rays, which encompasses or which includes a form of electromagnetic wave, which was kind of very interesting at that point. So you can imagine in 1850s or 1860s when this was kind of discussed in the scientific community, how impact it was having. And still this electromagnetic wave has the most engineering application. So from, if you look at any application that has actually resulted or used a lot in the engineering field, so from physics, this electromagnetic wave and Maxwell's equation is the most commonly used wave or the form that is used in engineering applications. Okay, so so then what we also were looking at, like how we can express these Maxwell's equation in terms of some potential. Okay, so which is your scalar and vector potential. So because we already know that we can define the electric field, or at least electrostatic field, as a gradient of a potential. And similarly, the magnetic field, we can also write as a curl of a vector field. So this is your vector potential, this is your scalar potential. So now when we talk about this electromagnetic the equations, okay, so Maxwell's equation, so can we also write these equations in terms of this potential, scalar and vector potential? So
Sir, what is A, sir?
A is the vector potential.
Okay, sir. Okay.
Okay. So vector potential means why we can write it like that, because we know that del dot B is 0. So, and we know if I take a divergence of curl of a vector is always 0. Okay, so this is a vector identity. And that's why, so in place of curl of a vector, so we are writing this some arbitrary vector A, and this is what we are calling as simply as P. And this is what, so here the potential is a vector quantity. Okay. Now, in fact, we can do that. So we can write the wave, the Maxwell's equation in terms of the corresponding the potentials, okay, and the form would look something like what we derived already in the last class. Uh, where so in terms of so we have basically two equations which can be used to express the Maxwell's four equations. So we have in Maxwell's equation, we have four equations, and using the scalar and vector potential, so we can write it in two equations, which is again a coupled differential equation. So the first one is del square phi plus del by del t into del dot A is equal to minus rho by epsilon naught. And the second equation is del square A minus mu naught epsilon naught del square A by del t square minus del the gradient of this del dot A plus mu naught epsilon naught del phi by del t. Or so here I'm using this notation from the book, from the your reading material. So instead of the potential V, I am writing it phi, and of course vector potential is A. So these are the two equations which is we are writing the Maxwell's equation now in terms of the potential phi and corresponding vector potential A. The the good thing about, I mean, there is some good thing and bad thing. So one thing is, of course, it looks very complex. Okay, so the four equations in terms of E and B were much simpler, of course, but in terms of phi and A, they look a bit complex, and they are like an inhomogeneous differential equation. Okay, so there is no like just simple differential term, second derivative. So there is second derivative, there is first derivative, then there is some constant term. So it is an inhomogeneous differential equation, which is not easy to solve, but nevertheless we can write the four equations in these two coupled equations. Okay, and one thing which also this one should be careful, that we know this potential is defined. It depends on how we define this potential. Okay, so because the potential, scalar potential, for example, you can define it with respect to a reference point. Okay, so the reference point can be infinity, or it can be anywhere. So it is up to you where you define your reference point. So that means the scalar potential can change depending on how you define the reference. So similarly, the vector potential can also change. But if we change this vector potential as scalar potential, it should not result in changes in the electric and magnetic field. So whatever form this electric field and magnetic field, or whatever, let's say if we say it is like a wave, okay, so it is like so it has some amplitude, it has some frequency, okay, so those things should not change even if I change the scalar or vector potential by any means. So this is where this gauge transformation is important. So what it means, the gauge transformation says that I can vary this phi and A without affecting the electric and magnetic field. So the magnetic field and electric field, they are the real physical fields that we encounter or we experience. But the scalar potential and the vector potential, they are not like observable. Okay. And this is, we are talking for this electromagnetic wave or any electric field and magnetic field that has a time dependence. Okay. So this, so if we change this phi and a, or do a transformation of phi and a, one is scalar, one is vector. So we are not going to affect or change this electric field and B field by any means. Okay, so this is the Gauge transformation, what means. And so how this condition can be satisfied? So we can choose the A as a prime A. So this is a new vector, so which we can write as a gradient of any, so A vector, the original vector potential plus gradient of any scalar. So this is not necessarily a potential or electric potential. It can be any scalar field. Okay, so this is any scalar function. And the corresponding change in the scalar potential. So scalar potential will also change, and the change would be like del chi by del t. So if the vector potential, if we change vector potential like this, so this will keep definitely the magnetic field invariant. Why? Because okay, somehow the page has changed, but nevertheless. So the scalar, if I change the vector potential like this, magnetic field will remain invariant because I know magnetic field is curl of A. So now if I change to A prime, so B is equal to now curl of A prime, which is curl of A plus this function. And I know, so let's say I'm writing this as B prime, so which is a new magnetic field, let's say we get due to the new vector potential, curl of A prime. So I will write it as curl of A plus curl of gradient of the scalar. And we know that the curl of a gradient of a scalar is always 0. So that means curl, so this will be simply curl of A, which is nothing but equal to B. So now B, which is originally was as a curl of A, and if I change A to A prime in this form, so then still the new magnetic field does not change really. So that means the magnetic field remains invariant or unchanged even if I change the vector potential. So similarly, if I substitute phi prime in place of phi, you can check the electric field also will remain the same. Okay, so this you can also check yourself. So this is just simply you substitute. But what is the electric field now? So electric field depends both on scalar potential as well as vector potential. Okay, so it has this form. Okay, so minus del A by del T. So now you just substitute this new phi prime there and you will see it will remain unchanged. Okay, so these equations that we are writing, so this gauge transformation that allows us to write these wave equations in terms of in terms of this inhomogeneous differential equations in terms of phi and a, or scalar potential and vector potential. Now, can we make it simpler? Because when you look at the form here, okay, so this looks pretty complicated. Okay, so this is where a gauge condition, certain gauge conditions were imposed so that you can write these equations, make these equations much simpler. And these gauge conditions do not really affect these gauge transformation. Okay, so the conditions are written in such a way or chosen in such a way that they are not going to change the overall electric and magnetic field. So gauge transformation, everything remains the same as we have discussed. Only thing, they simplify these equations. So there are two conditions, such conditions. One is known as Coulomb gauge, and the condition for this is del dot A is 0. So what it means now, how that is going to affect your equations. So del square. So now we just go back to these equations again. So the first equation here, this is the second equation. Okay, so the first equation, so del dot A is 0 means, so the second term will be 0. So I have del square phi is equal to minus rho by epsilon naught. And the second equation, if I put del dot A 0, so this term will be 0. And yeah, rest of the terms will be still there. So that in that case, so the equation will be del square A minus mu naught epsilon naught del square A by del T square minus mu naught epsilon naught del phi by del T is equal to minus mu naught J. So the first equation exactly resembles your Poisson's equation in case of electrostatic. And the second equation is still a bit complicated, but this is what the Coulomb gauge can simplify this wave equations, your electromagnetic wave equation, in terms of scalar potential and vector potential. Okay, the second condition, second one is known as Lorentz gauge, and what the condition is, so mu naught epsilon naught del phi by del T plus del dot A is equal to 0. So now if you substitute this, so the first equation becomes del square phi minus mu naught epsilon naught del square phi by del T square is equal to minus rho by epsilon naught, and del square A minus mu naught epsilon naught del square A by del T square equal to minus mu naught J. So if you substitute this condition in these equations 1 and 2 that we wrote here, if you substitute this condition, so you will get this two equations in case of Lorentz gauge. Okay, so this is the condition. Now the nice thing here, what you can see is we have actually separated or decoupled the equations in phi and A. So that means for so the first equation here just it in terms of scalar potential, and the second equation has only terms of vector potential, right? So there is no scalar potential term in this equation, and there is no vector potential term in this equation. So this is kind of simpler because we have decoupled this phi and A in two different equations. And even this one will be even much simpler if I take a source free or a charge free and a current free region. So for a current free and charge free region, so rho will be, so if I say it is a source free region, so rho will be equal to 0, J will be equal to 0. So source free means there is no source of electric field and your magnetic field. So source of electric field is always a charge distribution or charge density, that is rho, which is 0. And source of a magnetic field is always current and or the current density, that is 0. So in that case, these two equations become, so del square phi minus mu naught epsilon naught del square phi by del T square equal to 0, and del square, yes. Yes, any question?
Sir, sir, namaskar.
Yes.
Sir, ଆପଣ ଏ ଯୋଉ ମାନେ ପଢା ହଉଛି ତାର ଯୋଉ ଏକ୍ସାମ ରେ ଆମର ପାଟର୍ନ ଟା ସାର୍ କେମିତି ରହିବ, ମାନେ 100 ମାର୍କ ର ଆସିବ ନା କେମିତି କଣ ଆସିବ, ସେଇଟା ତ ଆମେ ଏବେ ଯାକେ ବି କ୍ଲିୟର ନାହୁଁ।
No pattern, I think you have to ask in a panigrahi sir. ତାଙ୍କୁ ପଚାରିବ ହେଲା କି?
ସାର୍ ତାଙ୍କର କିଛି କଣ୍ଟାକ୍ଟ ନମ୍ବର ବି ଆମ ପାଖରେ ନାହିଁ ତ ଇଗ୍ନୋରେ କିଛି କଣ୍ଟାକ୍ଟ ହିଁ କରି ହଉନି।
Okay. I think panigrahi sir, the students are asking what will be the exam pattern.
ମ୍ୟାଡାମ ପ୍ରାକ୍ଟିକାଲ ଯେତେବେଳେ ଆମେ କରିବୁ ଆପଣଙ୍କୁ ଜଣାଇବୁ। ଆପଣ ଇଗ୍ନୋରେ କଣ୍ଟାକ୍ଟ କରିବା ପାଇଁ ଚାହିଁଲେ ସିନା କରିପାରିବେ। You have to come and you send a mail to us. ଯଦି ପ୍ରାକ୍ଟିକାଲ ଯେତେବେଳେ ଆମେ ମାନେ ଆରେଞ୍ଜମେଣ୍ଟ କରୁ ଯେମିତି ଏବେ କାଉନସିଲିଂ କ୍ଲାସ କଲୁ ସେମିତି ପ୍ରାକ୍ଟିକାଲ କଲେ ଆମେ ଜଣାଇବୁ।
থিওরি ର ଯୋଉ କ୍ୱେଶ୍ଚିନ୍ ରହୁଛି ଆମର ମାର୍କ ଡିଷ୍ଟ୍ରିବ୍ୟୁସନ କେମିତି ମାନେ ଲଙ୍ଗ କ୍ୱେଶ୍ଚିନ୍ କେତେଟା ଆସିବ କି ସର୍ଟ ନୋଟ କେତେଟା ଆସିବ ସେଟା ଆମକୁ ଜାଣିବି ନାହିଁ।
Listen, MSc Physics is a first time program. This is
ଆଜ୍ଞା
the first year they had lunch. We also don't know about the MSc program, how much mark will come. But generally 20 marks or other exam हुए. So probably है अपना school को लिखोंदो. You write to school. School will tell you what is your, I mean, how much mark they will going to do the examination. Okay? You have a program
ସାର୍
guide.
ଆମେ
In program guide
କଣ୍ଟାକ୍ଟ
there is a mail.
କରିବୁ ରିଜିଓନାଲ ସେଣ୍ଟରରେ କରିବୁ ନା ଷ୍ଟଡି ସେଣ୍ଟରରେ ଯାଇ କଣ୍ଟାକ୍ଟ କରିବୁ?
ରିଜନାଲ ସେଣ୍ଟର ଆପଣଙ୍କୁ କହିପାରିବନି କେମିତି ଏକ୍ସାମ ପ୍ୟାଟର୍ନ ହବ। ଆପଣ ସ୍କୁଲର ଯିଏ ପ୍ରୋଗ୍ରାମ କୋଅର୍ଡିନେଟର ଅଛନ୍ତି ଆପଣଙ୍କର ପ୍ରୋଗ୍ରାମ ଗାଇଡରେ ଇମେଲ ଆଇଡି ଥିବ ତାଙ୍କୁ ଲେଖନ୍ତୁ। ପ୍ରାକ୍ଟିକାଲ ରିଜନାଲ ସେଣ୍ଟର କରିବ। ଯେତେବେଳେ ପ୍ରାକ୍ଟିକାଲ ଆମେ କରିବୁ ଆପଣ ଆମକୁ ଇନଫର୍ମ ଆମେ ଆପଣଙ୍କୁ କରିବୁ। ବିକଜ ଆପଣ ଟିଚରକୁ ପଚାରିଲେ ଟିଚର କିଛି କହିପାରିବେନି। ଟିଚର ଓନ୍ଲି ପାଠ ପଢେଇ ପାରିବେ। ଦେ ଆର୍ ନଟ୍ ବିଲଙ୍ଗସ୍ ଟୁ ଇଗ୍ନୋ। ତ ଆପଣଙ୍କର ଯାହା କ୍ୱେରି ଅଛି ୟୁ ରାଇଟ୍ ୟୁର ପ୍ରୋଗ୍ରାମ କୋଅର୍ଡିନେଟର।
ଆଚ୍ଛା ଓକେ ସାର୍।
Okay, sir,
So I
continue.
think just to add here, so don't worry about exam. So go through the class, whatever we are teaching, and also the class materials. And I'm pretty sure whatever in the in the exam it will be asked. So will be everything from the study material that is provided to you. So nothing beyond that. Okay. So this is when we write these equations for a source-free region. So what you can see is we can write even Maxwell's equation in terms of scalar and vector potential, just like a wave equation. These are also represent your electromagnetic wave equation, just like your E and B field. Okay, so this is the nice thing about Lorentz gauge. So where we can write the wave equation. Now, instead of in terms of electric field and magnetic field, we can write it in terms of the potential itself, phi and A. That is a nice thing about this Lorentz gauge. But it has also implications in electrodynamics, which leads to a special theory of relativity. So we will discuss it a bit later. Okay. So now we move on to another interesting part of this discussion. So which is like so far what we have discussed is how this electromagnetic wave looks like in vacuum or in space, free space. Okay. So whenever I am talking about free space, also the equivalent term is it is also vacuum. Okay. And so what we see from these wave equations that these electromagnetic waves, they can just propagate without any help from any source or anything. So they can just propagate within a vacuum. They can carry energy, they can carry momentum, they can exert pressure. Okay, so everything they can do just like a mechanical wave. But there is no such, let's say, they're also a transverse wave. So a lot of similarity they have in terms of, let's say, a mechanical wave or a spring when you vibrate. So very similar to that. But the nice thing is they can self-sustain. So a changing electric field is generating a magnetic field which is propagating, and similarly a changing magnetic field producing an electric field, and they sustain each other and propagate at a speed which is the speed of light in vacuum or in free space. Now the question is, how does this change, or is there any change when this electromagnetic wave enters into a material? Okay, so far free space is okay, clear. But what happens if it enters into the material? So how these electromagnetic equations or Maxwell's equation will change? So this again we kind of already touched upon before when we talk about dielectrics, or let's say a magnetic material. Uh, so we just have to add those information, and then we can write these electromagnetic equation or Maxwell's equation in a material medium. So the Maxwell's equation in material. Uh, so we know if we talk about a dielectrics, let's say, okay. So in dielectric material, so we know our del dot E, this will change to a rho free plus rho bound. Okay, so what is rho bound? Rho bound is your bound charges that originate due to this electric dipole moment. Okay, so if I take any atom, so simple, we are just depicting a simple picture here. So this is electron, the charge cloud, let's say, which is surrounds your nucleus, which is symmetric in nature. But if I apply electric field E, so what I will have a displacement of the charge center. So the charge center will be displaced, which will create a dipole moment P. And due to this dipole moment, so you have basically a local, or in the atomic scale, you have some charges. These are bound charges. This is what we call, and this leads to a dipole moment, and eventually what we call this. If I have n dipoles per unit volume, so if I have n electric dipoles per unit volume, so the polarization I can define as n into p. Okay, and your dipole moment is always, you will write in this case of, if we talk of electron, so it is minus E into the displacement d. This is the distance between your positive and negative charges. Okay, so this is the dipole moment that will be induced. And let's say if you have even a material which has already a dipole moment, like a polar material, so still the dipole moment will be there, so bound charges will be there, only thing the alignment will be along the electric field. So that means you have some bound charges, local charges, which are immobile. Okay, so this is just induced due to the electric field in a dielectric material. So definitely this bound charges, of course, they cannot exist in a free space or in a vacuum. They can only exist within the material. So now how this equation will modify? So we saw that del dot E, so we can write as, or we can define this rho B, this bound charges, as some divergence of a negative divergence of the polarization. Okay, so this is the bound charges that appear in this dielectric material. So in that case, your equation will modify accordingly. Del dot E, so is equal to rho F by epsilon naught, so minus del dot rho by epsilon naught. Okay, so this is in place of rho B, we are writing del dot P. And if we bring all the divergence term to the left hand side, so del dot E epsilon naught E plus P is equal to rho F okay, and which we defined with a new vector, a electric displacement vector, which we define as epsilon naught E plus P. So this is your electric displacement vector, which has an electric field plus the polarization that is induced due to this external electric field. And this is how your equation will modify within a material. And of course, your polarization also will be, most of the cases for a linear dielectric material, will be directly proportional to the electric field E, which is epsilon naught chi E, where chi E is your electric susceptibility. Okay. So what about the second equation? Okay, second equation, of course, will remain the same. That is fine. The third equation is curl of E minus del B by del T. So this is not going to change anything because we are not including any charges or any current here. So there is no bound charge, nothing will be here. So then this equation will also remain unchanged. Now, but this equation will now change. And what will be the change? Let's see that. Okay, so we said this is for a free or a vacuum or in free space. We said it is mu naught J plus mu naught epsilon naught del E by del T. But when you look at this current, so in a material, so of course you don't have this free current. So this J is due to the free current. Okay, so let's write it as JF, like we wrote it for the free charges, rho F. So this, what is the free current? Free current, I mean, so you just have a wire and then you pass a current through that to a battery. So you connect it to a battery. So whatever current is flowing, that is your free current. Okay, so that corresponds to your free current density. But within a material, so you can have a free current, but you can also have so bound current and current due to this bound charges as well. So you have current due to this magnetization, which corresponds to the magnetization of the material, and also you have a current due to the bound charges that just appear due to polarization, because you also have an electric field. So the electric field will give rise to a bound charge, and if I'm changing that electric field, so those bound charges will also move and they can also create a current. Okay, that would correspond to a bound current. So similarly, if I have a magnetic field, so in a material, so magnetic field can induce also a magnetic dipole. Okay, so this B field in a material, so like in a case of atom, we saw, so I have again the similar picture I have. So I have electron revolving around a nucleus. So this corresponds to, I can in a approximate as a current I, or current should be in the, yeah. So if the electron is going in this direction, so I say current is in this direction, which will correspond to a magnetic field B due to this current or a dipole moment. So this will induce a dipole moment M. So where your M is equal to I into A, and this dipole moment is due to induced your magnetic field within the material, and that also corresponds to a current which is known as a displacement. We called it a displacement current. Okay, so there are three types of current due to your magnetic field B and electric field E. So what we can write this as, let's say, the curl of B, so within a material, will be mu naught. So I can write as JF plus J bound plus J displacement. Okay. And of course, there will be the second term mu naught epsilon naught del E by del T. Okay, so the bound current, which is due to polarization. So that means, since this is it is, of course, the current is always proportional to your charge density. So here it is proportional to charge density. Yes.
सर आप जो मैथमेटिकल एक्सप्रेशन टा करछन्ते टिके तो टाइम लागिवो कैच अप करिया को बाकी हमको सिलेक्टिव देई दियंतु कि किछिटा इंपोर्टेंट क्वेश्चन तो आमे निजे ही सेटा करिया तो सुबि मैथमेटिकल एक्सप्रेशन टा टिके टाइम लागे
क्वेश्चन मु जानि नि कोन तेणु मु केमति देबी क्वेश्चन मु जानि नि कोन तेणु कोन कोइ कोइटा सब तेणु मो पई सब इंपोर्टेंट मो पई सब
इंपोर्टेंट तो एते लिमिटेड टाइम रे पढी होबोनी तो
नहीं सेथिपाई मेन जिनस ही कहूची आ बाकी तमे जोटा बही दिया हिची सेथुर पढियो
सर बही हमें पाइनु तो सेटा तो मेन प्रॉब्लम कि हमें हार्ड कॉपी पाइनु
नहीं से जो सेल्फ स्टडी जहां दिया हिची सेल्फ स्टडी पई जो दिया हिची ऑनलाइन पीडीएफ सेटर में पढियो
सर 130 पेज पीडीएफ
मैडम एटा सांकर सांग पढिबे क्वेश्चंस पे पत्र हम एटा पढे
हेलो
please don't tell professor, let him continue, otherwise other learners are facing problems. Let him continue.
ठीक है
हाँ okay so this is this current density that is due to this polarization. So it will be, since the current density is always will be proportional to the charge density, so we can write it is, and the current density is always, we can write as a rate of change of charge density as a function of time. So it will be this bound current density due to polarization will be just del P by del T. So this time rate of change of polarization will correspond to this current that is arising due to a movement of your bound charges. So similarly, what is the displacement current? So displacement current is due to the magnetization, which is written as curl of M. Okay, so this is so three types of currents you will have in a material. So one is the free current, that is that you connect to the battery, that current that flows, so that is the free current. Then there is a bound current due to polarization, which will depend on the change of the polarization as a function of time. And then there is the third type of current, which is due to this magnetic dipole that is arising, induced dipole that arises due to your applied magnetic field, so which is given by this term. So if you include all these in this equation, so you can now simplify. So instead of so you can rearrange and rewrite. So let me just do it quickly. So you have JF plus del P by del T plus curl of M plus mu naught oh sorry, so this is equal. So this is the first term and this is the second term. I'm just writing it here. So now we know this P, we can write as, oh sorry, so we can write this so let's rearrange a little bit. So curl of B, so the curl term I am taking to the left hand side. So curl of B divided, so I divide it by mu naught minus m. Okay, so the curl term I am taking to the left hand side, and I am dividing everything by mu naught. So B, curl of B by mu naught minus m. So mu naught will cancel out, and then I will have this term epsilon. Then so this del, sorry, no. So del by del t, I have epsilon naught E plus P, that is in the right hand side, and plus I have this term J. So which this is nothing but your magnetic field induction, and this term is your displacement, electric displacement vector plus J. So this is now how the fourth equation is now modified in a material. Okay, so to summarize all these equations in a material, so the Maxwell's equations will be is curl or del dot D is equal to rho F. So you have to specifically say this is a free charge we are talking about in materials. Del dot B will be 0, remains unchanged. Faraday's law remains also unchanged. But Ampere's law also gets a bit modified. So curl of H is equal to the free current in the material plus the rate of change of your displacement, electric displacement vector. So these are the modification to Maxwell's equation in a material system, which is due to, so which indicates that there is a additional charges and additional currents that are induced due to your electric and magnetic field, which are absent in a free space. And those additional charges contribute to additional polarization, which you uh, compute or calculate in terms of the electric displacement vector D. And so here you should also write these equations. So to complete this equation, so that you know what D means and what is H here. H is your B by mu naught minus m. So your original electric field induces dipoles, which creates the polarization, which results into a additional vector, electric displacement vector in the material, which is different from your original electric field. So similarly, the magnetic field that is original is there, that induces a magnetization, which corresponds to some due to which is equivalent to a electric current in an atomic scale, which induces a magnetization, and that creates a new field H, the magnetic induction, which are related in this equations. And they complete, so with along with these two equations and the four that we have written, complete your Maxwell's equation in a material medium. So sometimes also you will see D will be just simply write as epsilon naught into E. Okay, so for a linear dielectric material, and your H will be equal to B by mu. This is also for linear magnetic material. So here, what is epsilon? Epsilon is just the your permittivity of the material, and mu is your permeability of the material. So we are now going away from mu naught and epsilon naught. So if I take P is 0, so my relation will be D is equal to simply epsilon naught E, which is in free space. And if I say M is 0, so it will be H is simply equal to B by mu naught in free space. But within a material, so I will have some P, so P will be finite, M will be finite, and therefore that will also change this constants, the permeability and permittivity of the material. And this is how the electric field displacement vector and the H, they will be related to each other in this Maxwell's equation. Okay, so this is about so one can then also write the wave equation, so corresponding wave equations as well. So if I take a source free, and that means a charge free and current free region. Okay, so if I take a source free region here in a material, that means rho f is 0 and jf will be 0. So in that case, again, this Maxwell's equation will be just simpler. Del dot D is equal to 0, del dot B equal to 0, curl of E will be minus del B by del T, curl of H will be del D by del T, which also you can rewrite as curl of B, like what we wrote in. So you just write it down, and also you can then derive a wave equation, just like we did in free space. So you can also write a wave equation uh, in the material, but now this wave equation will change a little bit. So what will be the change? So it will be equal to mu epsilon and del square E by del T square. And that means now the speed of this electromagnetic wave within this material medium will be not exactly equal to the speed of light, but it will be reduced and will depend on the permittivity and permeability of the material, which you normally will write. So if I am writing it in terms of the relative permeability and permittivity and permeability, so it will be so mu naught mu r epsilon naught epsilon r, so which will be again the C by mu naught. So this is how the speed of light or the electromagnetic wave will change when it enters into your material. So it will be reduced definitely because of the permittivity and permeability of the material. So which also, like what you say, this also corresponds to your something which you are familiar in optics, that is known as your
Refractive index.
refractive index. Exactly. So this is your refractive index. So this is why we say the refractive index is different within a material, and also this refractive index also depends on what is your frequency and so on. Okay, so this is how the electromagnetic wave gets, so it will slow down once it enters into a material medium. Okay, so the next thing, yeah, there is not enough time. So if you have any question right now.
Sir, the last portion which you taught now is where in study material? I am not getting it. I am just searching for it.
It
Means
is
corresponding part in
in
unit.
uh, so what I have is, it is page number, so unit 5.
Unit 5. Okay.
Yeah. So I just moved to
Electromagnetic waves in different media. Okay.
electromagnetic waves in different. Yes, yes. So I did not discuss the AC conductivity part. So we will discuss in the afternoon session. So I'll start with that. So I just thought like just to complete. So how the Maxwell's equation modify in a material medium. So I just talked about that. And but the behavior, like how this wave propagates, so also we will discuss that, and how that affects the conductivity. So that also we will discuss. Okay. Yeah.
Sir, David Griffith book will also be good.
These are all, everything is in Griffith's book. Yes.
Okay.
So Griffith's book is, yeah, I mean, what I can also do is, I mean, are you aware of this NPTEL? Have you heard of NPTEL?
Yes, sir. They conduct courses, online courses.
Online courses. So there is already some related to electromagnetic theory. So you can search yourself in NPTEL. So there are a lot of video lectures already available. So any portion, so you go through your study material, and if you miss anything, so you can just refer to those sections in NPTEL. So nicely explained by many professors. So it will be very useful, because so you can understand it at your own speed, because these are all pre-recorded, so you can just upload it in YouTube. So if you are aware of that, it is good. If not, I can post few links. You go through that, and those some of the sections you can go through quickly, or some sections you can go slowly, depending on which part you understand or not. So you can learn on your own space then.
Yes, sir. That will be great, sir. Please
Okay,
provide
I
us the
will.
link in class.
Okay, I will share. Okay.
Thank you.
Anything else? So if not, so thank you. So we will meet again in the afternoon.
Thank you, sir. Thank you, sir.
Okay. Thank you,
Sir,
sir.
afternoon at 2 o'clock. Today afternoon
Thank
at 2
you.
o'clock, sir.
No, it is 4 to
Okay,
6.
fine, fine.